We have achieved great things. We have made giant leaps. We've gone far beyond what we thought was possible. But we have only just begun. Our future in space is unlimited, and it will benefit all humanity. But it will take hard work, new technologies, advanced financing models, and enabling public policy. The Beyond Earth Institute is creating a policy and legal framework to enable the creation of economically vibrant communities beyond Earth. We will engage all stakeholders on critical policy issues: property rights in space, norms of behavior, conflict resolution protocols, filling the technology gaps, exploring new financing mechanisms, and making space settlement an agreed goal of the U.S. and its allies. Beyond Earth is committed to the true purpose of why we go to space. Join us on this journey.
Good afternoon, everyone, and thank you for joining the Beyond Earth Institute for this webinar titled The Next Steps Towards Artificial Gravity. My name is Lauren Andrade, and I am the Director of Marketing and Communications at Beyond Earth. Over the next hour and a half, you will have the opportunity to hear the thoughts of our fantastic panelists on this timely and important issue. This panel is moderated by our very own Steve Hazer, Senior Technical Advisor at Beyond Earth. Steve is a Senior Space Systems Engineer, Architect, Space Habitat and Reusable Launch System Subject Matter Expert. He applies his 40-plus years of space and launch systems experience to leverage and expand human commercial and exploration activities in space. We are so grateful to have him on our team. We are also joined today by Dr. Donna Roberts, Deputy Chief Scientist at the ISS National Lab, who has served as principal investigator for several NASA-funded studies investigating the impact of spaceflight on the human brain during long stays in microgravity. We are also joined today by Dr. Dana Levin, Chief of Space Medicine at Vast Space, who works as part of a team building the first commercial space station and developing artificial gravity systems for long-term human habitation of space. Please also welcome Gary Hudson, Chief Architect at Gravitics Inc., Executive Chairman at Asheen Biotechnologies, and President and Trustee at the Space Studies Institute. Finally, we are joined by Dr. Ted Hall, an extended reality software developer at the University of Michigan. Ted completed his dissertation on the architecture of artificial gravity environments for long-duration space habitation, and is a senior member of the American Institute of Aeronautics and Astronautics, and was a founding member of its Space Architecture Technical Committee. With that, let's get started, Steve.
All right. So fantastic. If we could then go ahead and get started. I think the first thing that we should do is kind of set the stage with some basic discussion of just what is artificial gravity and how is it created. Ted, I think you've got a great intro on that topic, if you might be able to share that with us.
Contemporary physics posit that there's four fundamental forces that explain everything that happened in the universe: the strong nuclear, weak nuclear, electromagnetic, and gravitational force. Everything that happens is due to those four things. The strong and weak forces only operate at the scale of atomic nuclei. Most of what we experience in our life as force is due to the electromagnetic interaction, actually. If you've taken a class in chemistry or material science, you know that everything that happens between atoms and molecules is due to the electromagnetic force. And gravitational force, Newton's gravitational force, is sort of the odd man out. Among these four forces, three of them conform to the standard model for particle physics, and gravity is the only one that does.
We lost Ted. Let's go on here. With regard to artificial gravity, what are the, could either Dana or Gary address what is the current thinking on how such capability could be produced in the microgravity environment of orbital space?
I can speak to it, I guess.
Thanks, Dan.
It's anytime. That's what I'm here for. There's basically two ways to do this, and it's not really that we're creating gravity per se. What we're doing is creating inertia. And you're either doing that in a linear fashion, which is kind of like if you step on the accelerator in a car and you feel like you're pushed back in your seat. That's linear acceleration. That's the inert. That's the that will give you a linear force that mimics gravity if you go fast enough, but it requires a constant acceleration. And if you're not planning on moving anywhere,
Dan, if you could get a little closer to your mic, you seem a little bit away from the mic. If you could.
my mic is currently on my head, so I don't think I can get much closer to it.
Okay, that's a little better. What you did there, it's better.
Okay, I'll try and change some of the audio settings to see if I can increase the mic sensitivity, but for now we'll go with that. The other way to do it, aside from linear acceleration, is to do it in a rotational sense. So you're using angular momentum and basically spinning around in circles, literally. So you're not moving anywhere. You're just stuck in place. But that creates an angular momentum. So you're being pressed outwards, or you feel like you're being pressed outwards. But you're also inducing a spin, which gives you your which changes things from a linear perspective, which we're used to. So those are the two ways to really do it practically today, barring some wild innovation in physics that will allow us to change mass. And that's basically what it is. So it's either you're spinning a station or you're accelerating a vehicle. And probably the spin, if you're planning to stay in the same location, is the most practical way to do this. So I think that's probably the quick summary of it. If anybody else has other things to add.
Okay. So, one of the key things that folks who are asking, what could this capability, why is this capability potentially important for opening space to everyone and for human migration in general? Anyone can respond.
So I can perhaps jump in on that. Space and all the planetary surfaces beyond Earth that we know of are essentially hostile to life. Low gravity, radiation, thermal extremes of cold and heat. There's no breathable air, and so on and so forth. With our tech, we can mitigate every one of these risks except low gravity. No amount of human physics can change the surface acceleration of the moon or Mars. This is why O'Neill proposed spin gravity, which is the term I like to use, to describe the way human settlements in space would ultimately be developed, and that going to the bottom of a gravity well like Mars or the moon or so forth is less desirable in the long term for optimal human health. And when we talk about human health, there's actually two components of that. One is just our day-to-day health of an adult, but the one that's far more important from the point of view of the species is gestation, conception, gestation, and development from birth to adulthood. And we have very little understanding of the consequences of anything less than one gravity, which has been our constant companion for the last 500 million years, ever since life came out of the oceans. So that's why I say my position on the need for spin gravity, the debate is over in my mind. We have 60 years of experience with zero gravity or microgravity. And we clearly have to do better if we're going to have a long-term permanent human future in space.
That's a great, go ahead.
I'm
Dr.
sorry. I can speak to that a little bit as well. I want to start off by saying that my opinions and the thoughts that I expressed today are mine, and they're based on my many years of doing research and not necessarily reflecting my current organization, which is Center for the Advancement of Science and Space. But I did want to say that, as been expressed here, we know a lot about what happens with the human body in the 1 gravity environment, obviously, but also in the microgravity environment. And we know that in microgravity, there's deterioration of muscles and bones and cardiovascular health, immune function, essentially all aspects of the human body. And we have found ways to mitigate that through what's called countermeasures. And astronauts, for example, spend about 2 hours a day exercising to prevent muscle and bone loss and cardiovascular deconditioning while in spaceflight. But that's not really practical for the long term if the idea is to go to space to do science or to work or as a visit or as a tourist, then it's not really practical to spend most of your day exercising. And another thing that we found after years of spending time in space, and the longer that we spend in space, another issue starts to show up, which is a problem with vision. Approximately 70% of astronauts who spend time on the International Space Station have problems with their vision. And to the point where they have to change out the prescription of their glasses while in space, and they use these things called space anticipation glasses. They bring up stronger and stronger prescriptions of glasses. And when they get back to Earth and the doctors look in the back of their eyes, they see changes to the back of the retina and little areas of injury and swelling of the optic nerve that transmits signals from the eye to the brain. And this has been termed by NASA as spaceflight associated neuroocular syndrome. And we don't really know what causes it, and that's SANS. And the reason why I'm bringing that up is because of the countermeasures such as exercise, and does not help mitigate the SANS issue. So while the exercise might mitigate other problems such as cardiovascular and musculoskeletal, it doesn't mitigate the SANS issues. And so ultimately, it might be, and we need to do much more research, it might be that artificial gravity is the only way to keep the brain healthy in space. And so I think that's a very much a limiting issue that we're looking at right now.
That's fantastic insight. Really appreciate that that information. Along that topic, you indicated there, and Gary correctly indicated, we've got an awful lot of data on microgravity. I mean, we have 60 years, and now we're starting to get information on just more general people through some more recent flights. However, the question really has, what data has really been collected as far as, the in-space impact or effects of this induced spin gravity? There have been some attempts at putting centrifuges up there to spin and produce that kind of gravity. So what has been done to date in that area, and is it sufficient?
Well, I'll let someone else, I think Dana is probably going to speak about the studies that have been done in space, but I can say that there has never been a human-rated centrifuge in space, and so all the work that's been done has been done on animals.
So at this point, it's speculative based on animal research. Is that what you're saying?
Sort of. So yeah, there is not a lot of data on humans and how we react to the spin environments. Almost nothing has been done in space so far. Basically, what we have are basically anecdotal experiments or experiments that give us some estimations of Coriolis effects in very small rotation spins, like sitting in a chair and doing this. There were some experiments done on Neuralab and some done on Skylab with that kind of a spin. In terms of spinning spacecraft, there was really only one unintentional experiment that was done with the Gemini spacecraft when they separated from the Gina and accidentally induced a spin. There's nothing significant in terms of gravity there. The astronauts reported that they couldn't feel anything, but they were able to notice dust particles settling. That's it. Animal studies, there have been a number of them, and there was a pretty recent one on a small centrifuge with rodents that the results were just recently released, and I don't know them off the top of my head, so I apologize. I don't want to mis-summarize, but they're interesting reads that talk about how gravity gradients might affect living organisms at a complex level. And there's some interesting things there about, seems like that in general, more gravity is better. 1G is what we're all evolved to live in, so that makes the most sense. But there may not be as much of a benefit from lesser gravitational fields, which is interesting. It seems like there's certain systems react better to them than others. But from humans, most of the data we have comes from Earth-based analog studies, which were really done, I guess, from the 1960s through about the 1990s. There was some research in this that was done in a variety of places. Langley had a rotating space station simulator. There was another one that was, I think it was North American Rockwell, had a rotating space station simulator. And they basically put people in these giant rotating rooms and spun them. So if you can imagine being in a 1G environment, it's a cyclotron. If you go to the local amusement park and check that out. That's what they were doing. They were putting them in these things that would spin at various different distances and seeing how people reacted to climbing up ladders or moving within that. And it's as kind of as you would expect. People get a little bit nauseous and there's an adjustment period, and then they adapt in the same way that you do to most other places. So there's at least some data that says that we would do okay in a spin environment. It doesn't seem like there's anything that's prohibitive for it anyway. But there's nothing really in the spaceflight realm for humans, and that's why we need to do this. That's what the experimentation is.
Yeah,
Talk to me in a couple of years, though. I'll get you more information on that.
Go ahead.
I was just going to follow up a little bit about the ground-based studies. So what NASA does, obviously, it's very expensive to send humans into space, and only, around 500 humans have actually been into space. So we don't have a large subject pool to pull from. But what NASA does instead is they use ground-based analogs, as kind of been mentioned here. And one of them is called head down tilt bed rest. And that's when you take subjects and you have them lay in bed for extended periods of time with the head of the bed tilted down 6 degrees. And the reason for that is that when you go into microgravity, you don't have that gravity pulling down on your body. And so, again, you experience things like you don't have to use your lower extremity. So you experience disuse, lower extremity disuse. But another big issue is that the fluids in your body, when you're walking around upright here on Earth, experience what's called hydrostatic forces that pull that fluid down. And to simulate that, the lack of that in microgravity, which astronauts experience, and by the way, if you've ever looked at astronauts, pictures of an astronaut before they go into space, and then you look at a picture of them when they're in space, you'll see that their face is a little bit puffier in space, and that's called puffy face, obviously, and then their legs get thinner, and that's represents that fluid shipward up to the head. And so what NASA does is using this head down tilt bed rest simulates that fluid shifts up towards the head. And so that's a model for microgravity, and we study that. And the reason why I bring that up is there has been studies using the head down tilt bed rest as a model for microgravity, and then supplementing that with centrifuge to see if the centrifuge training mitigates the changes that you see in the human body during long-term bed rest. And I'll highlight one in particular that was recently done. It was performed in 2019. It was sponsored by NASA, and it was also ESA participated in sponsoring that. It was held at the German Aerospace Center, or DLR, in Cologne, Germany, at their MVHAP facility. It's a facility that they have where they can keep normal subjects at this head down till bed rest for long periods of time. In this particular case, they were there for 60 days laying in bed. Imagine that. And very strict. So they have people watching you to make sure that you don't lift your head up 24/7. They're watching, and you have to eat with your head down, and you have to you can't get up to go to the bathroom. So it's a very strict situation, and that's also they can simulate that those fluid shifts towards the upper part of the body and the disuse that happens in microgravity. And the thing about the MVHAP facility is that they also have a centrifuge there. And so what they did in the study, they had 24 subjects. They separated them into 3 different groups. One group of 8 subjects just underwent 60 days of bed rest. The next group of 8 subjects underwent 30 minutes a day of centrifuge, being exposed to the centrifuge, just continuous centrifuge for 30 minutes. And the next set of 8 subjects underwent 5 minutes of centrifuge 6 times during that day. So they still got this 30 minutes, but it was intermittent. And so the idea was, does exposing humans to the centrifuge during that time period mitigate the effects that they see? And what they found was kind of similar to what Dana was just saying, which is a mixed response. So some systems of the body responded to this 30 minutes a day. And for example, muscles of the back that normally wasted were preserved, so you didn't have as much muscle wasting. Another thing is that the brain changes in the brain that occur during microgravity has been shown in the astronauts, but also in the bed rest subjects that didn't have centrifuge. But the ones that did have centrifuge, actually that change did not occur. So it helped mitigate some of the brain changes. But then there were other parts of the body that didn't respond as well to the 30 minutes of centrifuge. And one of them is the changes to the eye. And so whenever astronauts experience SANS, or also when bed rest subjects undergo long-term bed rest as a model for spaceflight, they have changes to the back of the eye, in such that the back of the eye kind of flattens as that optic nerve swells. And that actually was not mitigated by the 30 minutes a day of bed rest. And so that just means that either in the continuous or the intermittent group. So that means that our prescription of what we were using for bed rest, maybe that 30 minutes a day isn't enough, or maybe the level of bed rest that they experienced wasn't enough. It was set up such that they experienced one gravity level at the center of mass of their body, but maybe since we're talking about brain changes, you need to have a centrifuge strong enough that you experience that one gravity level at the head to protect the brain and the eyes. So the point of all this is that the issue with artificial gravity is that we don't yet know what parameters we need. Do we need to have astronauts on the one extreme be exposed to artificial gravity throughout their whole stay, or on a trip to Mars, or on a lunar base? Or like a trip to Mars where we have to have the whole spaceship rotating 24/7? Or could we just have a part of the spaceship rotating for a certain period of time, and astronauts are experiencing this one gravity environment a certain period of time, or maybe it doesn't even have to be one gravity, or maybe it should be more than one gravity. So there are all those parameters that we can tweak in there. And so we really just need to do this type of research to figure out which ones we need to tweak the most. And obviously the best place to do this type of research is in space.
That's very insightful. So basically, it comes down to the question is we don't know how much gravity is needed for how long. We just don't know is the basic that I'm getting from that. And it's interesting, we're talking about the Earth analogs. Recently, I was involved in some discussions where the question was on Earth analogs as Ted started to talk, and I'm glad thank you for coming back, Ted. I'm glad you're back online.
I don't know how much you heard. Anyway.
We didn't hear much of any, just your intro, but you did talk about the various forces. And in a spin gravity environment, the discussions I was overhearing and part of was the discussion that Earth analogs have a basic flaw in that the environment can never eliminate the pull of gravity, no matter what the orientation of the people are. So you've got three forces working on you on Earth. You've got the spin-induced centripetal forces. You've got the outward acceleration or the acceleration response of the actual spin forcing you out, but then you can never get rid of gravity. And so but once you're in space, you don't have gravity. So the debate at this point, which goes to your point, Dr. Roberts, is we just don't know because we've never really had a large facility to do the type of human level research where we did not have the gravity component that is induced by the Earth. What do you folks think about that discussion?
I think that's accurate in saying that we don't have a lot of knowledge on this, and we haven't had that experience. What I would say to it is that as was highlighted by Dr. Roberts earlier, the cost of launching a mass and people into orbit is pretty high, or historically has been. The cool part of it is that recently we've been able to lower those costs by companies that use reusable vehicles or changing the fuels up and increasing engine efficiency. So we are actually decreasing those costs by a substantial amount. And that will enable or has enabled an increase in putting mass up in orbit, which allows us to put things that are large test beds and vehicles that we could potentially spin and gain some of this data. So I think that what's happening is historically this has been a conflict between building a station that is investigating the research that can be done in a microgravity environment versus putting the mass up there to figure out what artificial gravity would be. And there've all been engineering and economics trades about what was valuable. Nobody argued that artificial gravity research was not valuable. It was just argued about, is it doable within the resources or for the concepts of operation that we currently have? So what's happening now is we're starting to have more flexibility in what we can do. And that's giving rise to other experimentation, more facilities that we can begin to use to develop the data or the information that we have not previously had. So I think that we're getting to a point where we can actually start to do some of the experiments that we weren't able to do before, not because nobody was interested, but just because there's lower costs, the economics have changed, the vehicles have changed, and the research interests have changed. We've uncovered problems and challenges that spaceflight creates and realized that targeting individual problems that are all related to a single thing like microgravity or zero gravity environments may not be as effective or efficient as using that Occam's razor approach and targeting the problem of missing gravity, but being able to affect all of those different systems at the same time by that single intervention rather than piecemeal of lower body negative pressure and exercise and medications to fix disorientation and neurological changes. So I think that's where I would leave it.
what you were just describing, I've heard termed as the holistic approach to as far as response. It could cover many things at once. But another thing you were talking about that I really want to get into, because it comes down to probably the biggest problem. You talked about the cost of transportation and what is going to drive us to make these kinds of things affordable. I had a friend who was in business, and he always used to beat me over the head and say, "It's markets, markets, markets." So in that context, what do you think is the market potential for commercial space stations with artificial gravity? And if so, what are its long-term implications then as far as the overall expansion of not just research people, but industrial folks, families, and things like that? This is a general question throughout to the entire panel. Ted, you haven't gotten to talk yet. You got any thoughts on that?
I hope I'll have another chance to try to share my screen, but I don't want to sabotage it.
Yeah, let's move on.
I don't know how much of what I said previously was heard, so I can't. I don't have strong feelings about the market stuff, except that too many of the designs that I've seen are too simplistic. They only focus on the rotation rate and the gravity level. And there's this sort of feeling, well, if it doesn't, as long as it's not spinning more than 3 RPM or whatever, everything's fine. And they aren't attentive enough to the realities of the rotation and Coriolis forces and all these things. It's sort of like just basically too simplistic. You can have lunar intensity spin gravity, and it is not lunar gravity. It might be very, very different from lunar gravity in terms of how people, the forces that they experience as they move around within that thing. And there are just a lot of design details that need to be attended to make it comfortable. If we're talking about market value, we want people to be reasonably comfortable. This should not be a heroic endurance of one of these things, right? And so it's more complicated than just looking at the spin rate and just looking at the gravity level. For example, there's 4 variables that we typically talk about with spin gravity. There's obviously the radius, the rotation rate, the gravity level, but one that doesn't get much attention is the rim speed, the tangential velocity. And that turns out to be pretty important, because when you move around within that space, what matters ultimately is your acceleration, not the acceleration of the structure, but your acceleration in inertial space. And if your velocity is large, if your walking speed or climbing speed is large with respect to the rim speed of that spinning habitat, it makes a big difference. It's a distortion of the gravity, and it needs to be paid attention to. What we don't want is for a poorly designed habitat to be put up there and people inhabit it, and maybe it keeps them healthy and maybe it doesn't, but they just have a miserable experience because it wasn't designed well. That is not a good formula for market success. And so I would like to see more attention paid to the realities of rotation in the design of these things. It's too many engineers just look at that hard edge. There's all these versions of the comfort chart, and as long as I'm below 4 RPM, everything is fine. But if I cross the line, it's like I've jumped off a cliff or something. No, comfort is a fuzzy thing. The boundaries are fuzzy. And there are lots of things we can do with design to make it easier to adapt to.
Great input. Sounds like, again, the call for more input and research. Anyone else have any comments on that?
Well, I endorse what Ted said, because, I've seen a lot of proposals and even made a few for, say, lunar gravity generation at the floor of a rotating structure that's relatively small, say something that could be launched by a Starship in the near future. The problem, of course, is exactly as Ted has outlined. The acceleration at the floor is different than at your head, which is say 5 or 6 feet above the deck that the engineer is designing to, and that produces. I refer to it as ride comfort because basically I'm a space transportation guy, and I think about what is the comfort level of the passenger in a accelerating or decelerating rocket, going to space, coming back from space, whether it's suborbital or orbital flight. The last thing you want to do is create this, vomit-inducing environment that you never absolutely adapt to as you continue with your mission. And ultimately, the problem. Well, let me go back just for a moment to 2017. In fact, before that, when I became president and trustee of the Space Studies Institute, I looked at the things the Institute was doing and talking about, and I said spin gravity, artificial gravity was the most important question to be resolved technically, sociologically, physiologically, and so forth for permanent human settlement of space. And nobody seemed to be working on it. So I made a proposal for a thing called G-Lab, which was about a 100-meter diameter spinning Bolo type space station, specifically to answer the questions that we were talking about today. I presented at the American Society for Gravitational Biology in 2017, I think. The response was deafening silence. And I asked the question, why is NASA not interested in this? This seems like it should be right up their alley. And the real answer that I got was, this does not support a flags and footprints type mission to go to Mars. And so the agency has been hostile, and I will, use that word, hostile to the notion of doing anything with artificial gravity or spin gravity pretty much since its formation. And it's only the advent of commercial opportunities, Fast, Gravitics, other such companies, and the advent of low-cost space transportation, as has been pointed out by Dana, that is going to change that situation in the next 10 years. I fear NASA will be late to the party, but hopefully will be a customer that helps sustain the commercial enterprises that actually develop these initial laboratory-like environments where we can answer the questions we've been talking about today.
And I want to make one comment too when we're talking about markets. So there's a Danish architect who uses the phrase domesticating space. Johannes Torpe uses that term, which I really like, and I think it's important, to make the space environment something where a wide range of people can experience in a healthy and comfortable way, and as has been discussed just now by my colleagues. So if we're looking at space tourist and someone who's not a professional astronaut, then I think an artificial gravity environment is very important, and designing it, taking into account the issues that were discussed by my colleagues is very important. But then on the other hand, if we're talking about a space station whose purpose, for example, is to do crystal growth or bioprinting or other type of studies or manufacturing, are fundamental science studies in which a very still environment is required, then artificial gravity might not be appropriate. Because that could mess up your studies. So I really think that there is a place for, for artificial gravity in certain situations. And then there's a place where maybe we don't want to have artificial gravity. As a matter of fact, if our reason for going into space is to study the microgravity environment, then we don't want to have artificial gravity. We've shown that the microgravity environment accelerates aging, for example, and we can use that microgravity environment to study the impact of aging on tissue samples from the human body that it would take years to develop here on Earth, such as dementias and other disorders that would take years to study here on Earth, but we can study them in a very accelerated time and space in a microgravity environment. So maybe we don't have artificial gravity in that space station, but then on another space station where we want to study some of the impacts on the human body or other animals that we've been discussing here today, then we would want to have artificial gravity. So I think whenever we're talking about the value of artificial gravity and how it's going to impact the markets, we're really going to have to think about what are our objectives, what we're trying to achieve in that particular situation.
Excellent point. Excuse me. Excellent point, Dr. Roberts. I really appreciate your insight with regard to the potential incompatibility between a facility that has both artificial gravity and microgravity on board. I mean, the engineering problems I know I've run into, I'm sure that most of the other folks on this panel have run into, and that really have run into some problems. But in some recent discussions at some of the conferences, the idea of having, as you kind of pointed to, two separate facilities, call it the microgravity laboratory and then the hotel co-orbiting in close proximity. That was one approach to dissociating those issues and just, as we used to like to say in the football game, you just end run the whole problem. So there are a lot of discussions and questions out there on that. And in fact, I've really been impressed with this discussion with regard to the technical as well as the cost barriers. The launch cost, I know Gary brought it up, the majority of my career all the way from the Air Force was that launch costs were too high. And this reusability trend is, I think, going to make a huge impact ultimately. But let's go to one of the more interesting questions I wanted to bring up today, because it does have some fundamental bearing on the focus of a nation towards given goals, and specifically what might we see, or what do you see as possible policies or overall administrative statements that might be needed to catalyze development of either a commercial or a NASA artificial gravity research facility such as we've been talking about? And I open this up to the entire panel, obviously.
I think it's unethical to send people to Mars before doing low Earth orbit artificial gravity to see whether Mars acceleration is sufficient. When I talk about the history of space station concepts, actually, if you go back to the 60s, 50s and 60s, it was widely assumed that space stations would rotate for artificial gravity. It wasn't clear that people could survive more than a few hours or a day or a week in microgravity. But as we got more experience with microgravity and we found out it wasn't immediately lethal, then the mission changed. The mission that was originally Earth observation or astronomy or defense or something, and nobody really thought much about microgravity. But as we got more experience with it, microgravity became the mission. And so, and spacecraft design is actually kind of conservative. You know, we sort of figured out how to do things without killing people instantly. And it's like, don't rock the boat. You know, we know how to build capsules, and we kind of know how to keep people alive for 6 months or a year. But when we start talking about going to Mars, microgravity isn't the mission anymore. It's this thing, you know, for 6 months or 8 months between Earth and Mars, they're just trying to get to Mars as fast as they can. And they want to get there healthy, and they're landing on this rough terrain full of tripping hazards, and they're wearing heavy spacesuits, and they need to be reasonably fit when they get there. And now they're on Mars for months in this 1/3 gravity. We, you know, even if they're healthy when they get there, we don't know that 1/3 or so, 3/8, whatever, is going to keep them healthy. So to have them in microgravity all the way to Mars, only 1/3 of the gravity there, and microgravity coming back on a mission that lasts close to 1,000 days, that's just not ethical, I think. And if they're serious about going to Mars, they have to be serious about doing microgravity closer to home here. I mean, sorry, artificial gravity.
Thank you, Ted.
Yeah, I
Dana, do
can.
you have a night? Gary?
I was just going to once again completely concur with Ted. It puts me obviously at odds with Elon, but number one, I've never had much of an interest in Mars per se. And secondly, I have looked at sprint missions to Mars that would last only a year that require substantial amounts of Delta V and reusable vehicles that can tanker and refuel and so forth. Specifically for this reason, one thing that Ted did not point out is that you end up, when you come back to Earth, decelerating at, you know, many multiples of a G to return to Earth. So that adds even further to the biological complexity of conducting the mission successfully.
Go ahead.
I'm sorry, just to add another data point to what Ted was saying, and whether or not Martian gravity would remediate some of these changes. So in my research, I've studied what happens to the brain during long-term space flight for the astronauts on the International Space Station who spend 3 months to a year in space. And when they get back, we do brain imaging, and we see structural changes that have happened to the brain. The brain is shifted, and the fluid-filled spaces inside the middle of the brain have enlarged. And so the question that I always get, and those are on the MRIs, right, when we take brain imaging right when they get back within 2 to 5 days of being in space. But the question that I always get is, what after some time back on Earth? So after months back on the 1 gravity environment of Earth, we've looked at it up to 7 months to a year afterwards. My colleagues in Russia published a paper, and then more recently, a colleague of mine in Houston published a paper showing that that even after a year back on the 1 gravity environment of Earth, that the structural changes have only partially returned to baseline. So if that's what happens in the 1 gravity environment of Earth, then that really, you know, raises questions about what would happen on a 1/3 gravity of Mars. Would that be enough to promote return to baseline or not? So it still really raises that question.
Dana, do you have any thoughts?
I think I agree with pretty much everything everybody's saying. We don't know a lot about this, so we need to do things in a way that's going to give us the information we need to get there safely. Ultimately, the goal is to keep people healthy and alive and get them back intact. So, or have them colonize intact. In order to do that, we need to take a stepwise approach. We need to understand a little bit more about what how microgravity affects things, and also how artificial gravity can be used as a countermeasure. Ultimately, that's going to require research and experience. And it's a lot easier to get a larger number of people up in low Earth orbit than it is to get a large number of people over to Mars, and a lot more ethical in the short term anyway. So I think I agree with everything that's been said so far.
Thank you for those insights, folks. With regard to, we're kind of coming up on the point where I'd like to, normally we don't have a lot of time for giving each of the panelists a soapbox, as it were, for making presentations with regard to the topic that we're talking about here. So I'd like to give each of you 3 or 4 minutes each, at least, to give us any insights, perhaps identify what other issues, concerns do you see that might be related to this particular topic. And anybody can start, and we'll just go down the line from there. Or do I have to call on somebody?
All right. If nobody starts out.
Gary, come on, Gary.
I still want to share slides, but I don't want to sabotage the whole thing again. So I'll go last. I'll go last, and then if it dies.
Okay.
So these will be random thoughts. First off, I obviously think there's, huge potential in spin gravity, since I was a co-founder of Gravitics, which is a company that wants to be a general contractor to build such facilities. We have no ambition to operate them, but we would like to work on building them. I think it's very early to try and quantify market potential. This was a question we were thinking about, but I do want to say that money is going to drive this, right? I mean, we can have all the discussions we want about human biology and the technology and the design of such facilities, all of which are vitally important to have. But we're investing as a community, call it a tech community. We're investing heavily in so-called future technologies such as artificial intelligence. Elon is currently raising like $6 billion for an AI venture. If we're really serious about making the high frontier of space into a home for humankind, we need to be thinking about how to raise and spend comparable amounts of money. I'll tell you, I don't know how to do that. But the broader question is, once you start answering some of these spin gravity questions, and you want to move into things like large-scale O'Neill size space settlements, what's the long-term implication for the expansion of humans into space on a permanent basis? So I'd like to leave everybody with, at least with respect to my comments, with this thought, which is not mine. The real question is, what drives this? What's the economic underpinning? O'Neill thought it was satellite solar power, that space settlements would build satellite solar power stations, sell the power to Earth, and that would be the engine that drives the economic expansion. But recently being in the last 10 years, a good friend of ours, Jim Bennett, has pointed out that at the time of the American Revolution, 3/4 of the bottoms, the hulls of the British Empire fleet, both her men of war and her mercantile fleet, were actually not built in England because there weren't trees sufficient to make masts there any longer. It had been mined out, as it were. They were built in New England, a British colony, 3/4 of the fleet. That, to me, suggests that the market that drives the building of space settlements is space settlements. So you build one, it builds the next, and the people in the first space element are employed by the, as contractors to build the next, and so on. And this is how you get, a massive human population off Earth over the next several centuries, that, where the population of space might actually exceed the population of Earth in terms of gross numbers. So that thought is something I definitely wanted to share at this webinar, because I think it's a unique one, and all kudos to Jim Bennett for raising that at a conference we, Space Studies Institute, sponsored a couple of years ago.
Very good point.
Hey, Steve Wolf here. If I may use my president's prerogative for a second. Gary, we could end on that note. I mean, that was very inspirational. And that certainly represents, I think, where we want to go in terms of human habitation. But I am noticing several comments in the chat field, and I want to give our audience some recognition. They're particularly interested in the actual projects of gravitics and VAST. And we're wondering if you could talk about your specific vehicles for a few moments, and then, what your market potential is, what your timelines are for those particular vehicles, because that's what's happening with regards to artificial gravity, in the real world in the near term. So that's, so we're excited to hear about that, if you would, if that's okay, Steve.
Oh yeah, definitely. And we anything that you can share, let's just put it that way.
Yeah. So Dan, if you would, and then maybe Gary, you could come back on and talk a little bit more nuts and bolts about gravitics.
Sure, I'm happy to. The first thing that VAST is attempting to build is Haven 1. It's a 4-person space station that is going to be investigating both microgravity. Most of its lifespan in orbit will be a microgravity station, as well as partial gravity from spin-based operations. It is more or less the thing here behind me. Although this is a concept rendering, the actual structure of the vehicle has changed significantly since that rendering was made. But it's designed to basically, if you picture it as a long stick, it will spin end over end to generate that gravity. That's the platform, and VAST is basically interested in building a platform for the smart people of the world out there who are brighter than me to come up with ways to explore this. So we have our own internal investigations on this to try to figure out what the business case is for both microgravity and for artificial gravity. We also have our own research projects that we're interested in. But to be pedantic, space is much bigger than any of us. It's big enough for all of us, and it's going to require a lot of intelligent people to work together to come up with interesting ideas to explore their concepts. So both the business side of it, the economic side of it, the research side of it, and not to limit it, the fun side of it, the experience of people going up there and experiencing what these areas are. That's what we're interested in creating. We want the platform to exist so that we as a species can explore it. The specifics are proprietary often within the company, but we want this to be we're building a platform, and we want to have it available for people to use. That's essentially what the goal of the company is. And we want to figure out how to do it safely. So my interest specifically is as a physician. I can't speak necessarily to the business side or the engineering side as much as some of the engineers or business people could. But my interest and the company's interest is to do this in a safe way. So we have to figure out how to do this without putting people at risk. And what are the risks that we introduce by doing something new? What are the risks that we mitigate by doing something new? And then understand through those how we can develop a how we can grow and as a species and actually develop systems to live off the planet. So that's I guess the quick high level summary of what's going on.
Yeah, so putting on my gravitics hat, or actually my gravitics shirt, I guess today. First off, I'll admit to a degree of envy because VAST doesn't have to do what gravitics has to do, which is go out and hunt up investors at quite the same level or rate. So that tends to limit our ambition. We basically have to learn to walk before we can run into the direction of building a large spin gravity facility. For us, the challenge is principally an engineering one of fabricating low-cost structures. We like to think of it as building structures in a more bespoke shipyard, like a yacht, a high-end yacht or something like that, as versus an aerospace style approach to construction, because that's going to be necessary given the large mass of these structures to limit the cost of materials, the cost of labor, and so forth. If you're spending $1,000 a pound making orthogrid or isogrid or composite structures, and ships are being built even for expensive yachts for billionaires for $10 a pound, you want to be closer to that shipyard experience than to a Boeing or an Airbus or military jet style experience. So cost of fabrication is something that drives my thinking as chief architect of gravitics. But ultimately, it will be customers coming to us saying, we want to build a spin gravity station for research or for habitation or for tourism or whatever, that will drive our business plan and strategy. So we are always talking to such customers, but we don't have at the moment a specific plan to implement a spin gravity capability. I hope it happens within my professional working career, which is sometime in the next 10 years. But in the end, it comes down to, as I said earlier, no bucks and no buck Rogers.
Thanks for those insights. One thing that I might add from my personal experience of trying to do space tourism, as an engineer, I think Ted had put it very importantly. Sometimes from one person's perspective is not necessarily the perspective of customers. And in regard to adventure tourists, which is kind of the high-end folks we're talking about here, or people that like to do Arctic cruises, things like that. Interestingly enough, yeah, they want to be comfortable, but they want to experience new and different things. And so having something that is not normal is not necessarily bad. But the point that has been made is that let's not make it so bad that it's not an experience that they want to come back and try again, I guess, is an input. Well, thanks for those insights that you guys provided. We got about 10 more minutes. I'd like to give Dr. Roberts and Dr. Hall their moment on the soapbox before we finish this excellent exchange we've had on the webinar. Dr. Roberts?
Yeah, thank you. So again, I think for me, that the importance of artificial gravity is as we look to opening up space and bringing more and more people into space and from more diverse populations. We know that long terms and microgravity has impact on the human body. We don't know the full extent. We know, for example, in my own research that there are changes to the brain. I've also documented in the head down tilt bed rest model some changes to blood flow to the brain. And maybe that's great for a nice, healthy, fit astronaut, but it might not be perfect for a 70-year-old who is that space tourist that you were just talking about, Steve, who can afford that big ticket to come into space. So the worst thing that could ever happen is that if we had some kind of medical emergency that happened in space. So I think, it's very important that we provide a safe environment for those tourists traveling into space. And, again, this wider diversity of population. On the other hand, if we are a NASA astronaut who is fit and healthy and is planning on doing sensitive experiments in space, then perhaps that's not exactly what we want. So astronauts, my good friend Mike Barrett, who's up on the space station right now, has said to me in the past that artificial gravity, being in microgravity actually makes more usable space in a space station. So for example, if you have artificial gravity, now you have a floor and a ceiling and walls, whereas if you're in microgravity, you have more room to move around in an already cramped space station. And in addition, some tasks might be easier in microgravity, but then on the other hand, such as moving a big piece of machinery around, but then on the other hand, doing simple tasks such as manipulating fluids and stuff in experiments is much more facilitated being in an artificial gravity environment. So I think that what we're trying to accomplish really needs to be taken into account. But ultimately, our civilization, our human species has developed and evolved in a one gravity environment, and understanding how altering that and the impact that it has on the human body is just giving us so much more insights, and not just studying it at a microgravity or one gravity environment, but multiple gravity levels in between, I think will open up even that much more of an insight. So I'd love to see those type of studies being done in the future. So thank you.
Yeah, the old question, how much gravity is enough?
Exactly.
Ted, what are your thoughts then, closing thoughts? And then we'll give it back to Steve for closing remarks. Steve Wolf.
Well, I'm really sorry I couldn't share my slides, because what I really have nice pictures to show is that Newtonian gravity is actually irrelevant. It's neither necessary nor sufficient. It's all about mechanical acceleration. And so we have a high confidence that spin gravity works because it's acceleration. And in the end, we don't care about gravity, we care about weight. And weight comes from the upward push of the floor, not the downward pull of gravity. Rotation introduces interesting effects, and we need to pay more attention to those when we design these things. I mean, if we're talking about tourism, yes, people want new experiences, but they don't want to be miserable. And even if we look at, adventure camping, right? Camping is, they talk about what, I forget, glamping, right? Luxury camping kind of.
Glamping, right? Yes, glamping, yes.
Yeah, so, you go to the sports store and you get nice, you don't get heavy canvas tents, right? You get nice lightweight stuff that is durable and it keeps you comfortable and dry, and nobody wants to be cold and wet and soggy on their camping trip. And so there's things we need to do. We need to pay attention to the design of these artificial gravity habitats to make people reasonably comfortable. It's not going to be like Earth. It's not going to be like the moon or Mars. It's going to be a different experience. And as you said, people want that. Also, I'm not too concerned about the fact that people aren't immediately comfortable. The argument, it has to be a mile in diameter, people will get ill. And what they forget is that people get ill in microgravity, right? It takes 1 to 3 days to adapt to microgravity. So if it takes 1 to 3 days to adapt to artificial gravity, at least you're more healthy after going through that adaptation. So it doesn't have to be immediately healthy. We want an educated clientele. We don't want, frankly, ignoramuses going into space expecting it to be like Earth when it's not. You know, you don't want ignorant people climbing Everest because they're going to die, right? We want to make sure that the people we send are comfortable, are well informed about the environment they're going to, and they've got a little bit of an adventurous spirit. But we have to meet them as designers. We kind of have to meet them halfway. We have to do whatever we can to design it in such a way that the Coriolis forces work with them and not against them. Yeah, and I have a lot of pictures. I wish I could have shared my screen.
We'll
I'll
have to
stop
catch
there.
you at the next conference.
Yeah.
Or maybe invite you to our conference. Well, maybe we'll talk about that afterwards. Okay. Ted?
Okay. Yeah. Okay.
Yeah. So definitely, this has been an exceptional discussion from my point of view, and I think we brought out some remarkably interesting perspectives on the next steps towards the artificial gravity. Not the least of which Ted just kind of indicated in the fact that the requirements that are going to drive the designs are going to come not just necessarily from government customers, but from possibly commercial customers. And so I guess that's going to be the challenge for those folks working those designs, and perhaps us at the Honored Institute to understand better as well. With that, I'd like to thank all of the panelists and leave it over to Steve Wolf for any closing remarks.
Hey, Steve, that was a fantastic program. Thank you so much. And thank you to all the panelists. I think, as you could see from this conversation, that that artificial gravity can play an enormous role in the health and survivability of humans in space. It's an area of research that has been underfunded and paid far too little attention to. And it is something that can be so transformative as we look to expand human presence in space. That's why BE has put so much attention on this. I should also mention that the working group that Steve Hazer is actually running is running for us is focusing particularly on artificial gravity with the intention of making a recommendation to policymakers that we elevate artificial gravity research within our space program. I do want to acknowledge all of the attendees and the questions that were put into the chat field. We were not able to get to all of them. I think some of them are very interesting, looking at microgravity or low gravity in the asteroid belt, and how do we going to deal with many of these issues. So really appreciate that. Could not get to them all. I do want to acknowledge that I put in the chat field a link for our next webinar that will take place on June 27th. It'll be chaired by our own Courtney Stad. And it will be on commercial market forecasts. Are they credible, and who to believe? And this now is going to get closer to home, or I should say, it's an important discussion as we try to understand what that market's going to be. And there's going to be a market for commercial space habitats and for habitats that provide variable gravity and so forth. So certainly look forward to that. And you can take that down. And then with that, I want to thank you all again. I want to thank Steve Hazer and the panel for being here today. And with that, I will let you all get back to your afternoons, and appreciate your joining us today. We'll see you next time. Bye now.